All right, calculus. Today we're going to be looking at linearization. The chapter section is 5.5 called Linearization, Sensitivity, and Differentials. Really, out of those three topics, we're only going to talk about linearization and differentials, really. So let's get started taking a look at what the heck is linearization. And if I had to tell you something about linearization, I'd say don't take it. It's not really a difficult process. We're just, taking what we knew from Algebra 1 and we're putting it into the context of calculus. So this is really an Algebra 1 section as far as I'm concerned. So we've got Night of the Living Dead, perhaps one of the most famous zombie movies now. So the start of the modern zombie film is almost universally accepted to be the 1968 George Romero classic Night of the Living Dead. Starring Dwayne Jones and Judith O'Dea, the story follows 7 people trapped in a rural farmhouse in western Pennsylvania under assault by a growing group of cannibalistic undead corpses. That's kind of the basis for every zombie movie out there at this point. Since its release, critics and film historians have interpreted this, The Night of the Living Dead, as a subversive film that critiques 1960s American, international Cold War politics, and domestic racism. All of those things are in there. I think it's really interesting to understand or think about how actually that fits in. So the film and its successors spawned countless imitators in cinema, television, video games, all of which borrowed elements invented by George Romero. So, great film if you want to see where all of these zombie films come from. Go check out Night of the Living Dead. So I said this was an algebra section, and I kind of mean that. We're starting off with the point-slope formula from algebra. Here's the point-slope formula. We're going to make a slight adjustment to that formula by bringing the y naught over to the right side of the equation. By doing this, we create for ourselves a function for y. So y is equal to this function. Now remember, x naught and y naught are two coordinates. Sorry, it's a set of coordinates that are known. Now the calculus comes in here when we realize that instead of slope, here, m, we could be putting dy dx. Okay, so we're going to put the slope here. And more specifically, dy dx is the slope at x naught, y naught. So now we have a tangent line equation. Dy dx is the slope at x naught, y naught. And so y is equal to y naught plus dy dx, x minus x naught. Let's look at this problem. What is the equation of the tangent line to f of x equals root x plus 1 at x equals 3? Well, they don't give us a y-coordinate, and we're going to need a y naught, the y-coordinate. So the first thing to do is just substitute 3 into f of x, and we quickly find out that f of 3 equals 2. Next, we're going to take the derivative of f. That gives us 1 over 2 root x plus 1. And if I substitute 3 into that derivative, I'm going to get that the derivative evaluated when x equals 3 is 1/4. So let's pause here and think about what that means. And this says to me that the slope of the tangent line at x naught, y naught equals 3, 2 is 1/4. So now I have all the tools I need to create the equation of that tangent line, which you've probably already done before. We'll get this same equation that we had before, y equals y naught plus dy dx, x minus x naught. Substitute those values over here for y naught. We have 2. Over here for x naught, we have 3. Then over here for dy dx, we have 1/4, which is from here. So all that together gives us the equation of the tangent line. Shouldn't have been a difficult problem. It wasn't a difficult problem, so let's move on. And now that we have the idea of that tangent line, let's take a look at this graph again. Now this right here is the graph of y equals root 1 plus x. And I'm going to zoom in here to 3, 2. So here's the first zoom, and here's the second zoom. Now you may not have, maybe you don't see it in the first one, but in the second zoom right over here, something should be kind of obvious. And that is, it doesn't look like I'm looking at a square root function. This looks like I'm looking at a straight line, linear. And that realization is actually really important for us. And the realization should be, if you zoom in enough, if you look close enough at any coordinate on a curve, then the graph at that coordinate is going to be a linear function. Okay? It is the same thing as a tangent line. So that tells me that I can say that this is true. F of x is approximately equal to, and that equation on the right side is the equation of the tangent line. The function is equal to the tangent line, or it's approximately equal to the tangent line. The only caveat to this is that x has to be close to x naught. In other words, if I'm looking at if x naught equals 1, then this is true for x equals 0.9, 0 or 1.1, 1.15, but it's not true for x equals 2. So the further away from the point of tangency is what we call it, the further away from that x naught, y naught, the worse the linear function does for approximation. So now we're going to use that same thing. We're going to use the linear tangent line approximation for f of x equals root x plus 1 at 3, 2 to estimate 2.8. So a basic question you want to ask is 2.8 close to 3? And that answer is yes. So since 2.8 is pretty close to 3, I should get a meaningful approximation of f of 2.8. So first thing to do on this is to ask, what is the function that we're approximating? Okay, well, we're approximating f of x equals root x plus 1. Now the next thing to ask is, okay, now that we know what we're approximating, do we have a point of tangency? Do we have a coordinate that we know, or do we have a place where we know both the x coordinate and the y coordinate? And yes, there is. We know both the x coordinate and the y coordinate at 3, 2. Now we're going to do basically what we just did in the previous exercise. We're going to create the tangent line of the function. So we start with the derivative. So the derivative of f of x is 1 over 2 root x plus 1. And then we evaluate the derivative at x equals 3. And maybe you haven't seen this over here, but when we put the line and then an x minus 3, that means we're evaluating at x equals 3. We're going to get 1/4. We already did that work in the previous example, so that's not shocking. So we're going to use the slope to create the tangent line. So the tangent line, of course, what we saw on the previous example, that's just 2 plus 1/4 x minus 3. And then to approximate, we're just going to substitute into the function. So we'll substitute 2.8 into this. Sorry, we're going to substitute 2.8 into this tangent line function. And what are we going to get? Well, we will get 2 plus 1/4 of 2.8 minus 3, and that gives us 1.95. Great. Now we have an approximation for f at 2.8. Now you might be asking, well, I know the function already. Why bother with the approximation if I know the function? And that's a question that I often ask myself too. Why am I bothering to approximate the function that I already know? Well, to answer that, we have to think there are times when it is easier to approximate the function than to actually not, than it is to evaluate the function. And that's in cases like, even this one. Would you rather do a square root of 2.8, or would you rather just evaluate this linear function? Okay, now think about it. What if you didn't have your TI-84 with you? Would you rather evaluate this function or take the square root of 2.8? I think you would rather do the linear function. And that's kind of where this comes from. So how close are we to the actual value of f of 2.8? Now this is going to assume that we know how to evaluate the square root of, 2.8 plus 1? And if we can evaluate that, then we can see how close we are. So the actual value of f of 2.8 is 1.94935. That comes from a calculator. Here in calculus, when we want to quantify an error, we're going to use the absolute value of the actual value minus the approximation. So right over here again, actual minus approximation. So let's line those two numbers up and see the difference that we get. Here we have the actual value is 1.949 minus our approximation of 1.95. And I get a value that is really small, 0.0064. So is that within your expected tolerance? Well, that's definitely within the expected tolerance for the AP test, 3 decimal places. So, we found, number one, this process to be pretty easy to find the tangent line. The tangent line approximation was pretty easy to get, and it was close enough for us even for the AP test. So is there a difference between the tangent line approximation and the square root function? Yeah. For this case, not really. Not if we're within or really close to f of or at x equals 3. So that's one reason why we're doing this. So let's try this again. We're going to use a tangent line approximation. Now the tangent line approximation that you see here, that is a synonym for linearization. Okay, linearization is just using a tangent line to approximate. So let's figure this out. Start by deciding what function we're going to approximate. Of course, we want to approximate the square root of 119. So we should use y equals the square root of x. Next, we're going to find a point of tangency. We want to pick a number that's close to 119 where we know the square root. So the square root of 119 is pretty close to the square root of 121. So we can use this as our approximate, as our point of tangency. So when x is equal to 121, the square root of x is equal to 11. That's our point of tangency. Next, we're going to be creating the tangent line. So if y equals square root of x over here, if y equals the square root of x, then dy dx is equal to 1 over 2 root x. And then we're going to evaluate that derivative at the point of tangency. At the point of tangency, then, the derivative evaluates to 1 over 2 root 121, which is 1 over 22. Next, we're going to figure out, we're going to use this slope, and we're going to use x naught, y naught, and we're going to figure out our tangent line equation. So we've got f of x equals y naught, and what was y naught? That was 11, plus the slope, and the slope was 1 over 22, multiplied by the quantity of x minus 121. 121 was our x naught. And that's where those values come in. Finally, in order to evaluate, or in order to figure out the value of the square root of 119, we just substitute 119 into the tangent line equation. So the square root of 119 is approximately equal to 11 plus 1 over 22 multiplied by 119 minus 121. And that gives us 10.909. Okay, well, we could ask how close we are, but I think from here we're just going to move on. So there is a special case here. This being a special case means that, you know, your usage of this might be limited. But in a special function like y equals 1 plus x to the k power, and if we center it at 0, meaning 0, I think it's going to be 0, 1, 0, 1 is going to be our point of tangency, then we could just use y is approximately equal to 1 plus kx as our tangent line. So it's a very special case, and that comes from actually the derivative. So let's see. Let's estimate. We're going to use this special case to estimate the cube root of 0.98. Okay, so the cube root of 0.98. So what would that estimate be? Well, off the top of my head, if we're taking the cube root of a number close to 1, well, then I suppose the cube root of 1 is 1. So the answer here should be somewhere around 1. Start by deciding on a function to use for approximation. Now, hopefully it's clear. Maybe it's not. But we're going to use the function, the cube root of 1 plus x, because we want to use this as a special case. So because we want to use a special case, that makes us the function y is equal to 1 plus x to the 1/3 power. Notice that in this case, k is going to be 1/3. Okay. Now, we're going to decide on our point of tangency. And in this case, I suppose we're going to pick x equals 1, or x equals 0, because when x equals 0, y is going to be equal to the, let's see, if I plug in 0, substitute 0 here, I'm going to get 1 plus 0 to the 1/3 power, and that's just 1. Okay, there's another reminder that this is a special case. This is, you know, just one application of that tangent line equation. Normally, we would create the tangent line function, but since this is a special case, all we really need to figure out is the value of k. And we already said that the value of k is 1/3. And because this is a special case, when we create the tangent line, we can just use that value of 1/3 and say that f of x is approximately 1 plus 1/3 x. So if I want to get 0.98 and I have 1 plus x, well, I need to turn 0.98 to the 1/3 power. I need to turn that into 1 plus something to the 1/3 power. So what would that something be? Using techniques of solving, I think you can see that in order for this to work, these two bases, 1 plus something, has to equal to 98. And if that has to be true, then x has to be equal to negative 0.02. Which means that the cube root of 0.98 is going to be approximately equal to 1 plus 1/3 of negative 0.02. Now that is the x that we decided on earlier. So there's the x. There's x equals 0.02, negative 0.02, And there it is again. What does that evaluate to? And that's 0.99333. So close enough. All right, so that's our special case. And what makes a special case special is that it's easy to do, but it only works for a limited number of functions. So that actually brings us to the end of day 1 here. So the important idea is under sufficient magnification, every function is approximately linear. I love that because it says every function, and I mean every function. If you zoom in enough, it will be a straight line. So you can use a linear approximation to approximate that function close to a convenient point of tangency. Okay? So the linear approximation, we already have that equation. We talked about that at great length. The linear approximation is y equals y naught plus the derivative at x naught y naught multiplied by x minus x naught. And then there is this special case which we just discussed. Now, to check our understanding, we have this. A plastic zombie figure is dropped from the top of a 100-foot lift of a roller coaster. Estimates for the height of the zombie at select times t is given in the table. So let's estimate the height at t equal, or the derivative of the height at 1.7, and then use that estimate to approximate the height of the zombie 2 seconds after it's released. So the first part, estimate h prime at t equals 1.7. And then the second part, approximate the height of the zombie after 2 seconds. Okay. H prime at 1.7 and the height at 2 seconds. So let's see what we do here. How do we estimate a derivative? Okay. And the answer to that is, to estimate a derivative, we need to find 2 points that are close enough to the point that we want to estimate the derivative. In this case, our point of tangency, 1.7, and then use a slope formula for those 2 points. The derivative is the slope. So I think you see that the 2 points that are closest to 1.7 are these two right here, 1.3 and 1.7. So we're going to use those points, and we're going to find the slope of the tangent, the secant line that connects them. So we've got h prime at 1.7 is approximately equal to this 54 right here, 54 minus 73 on top of 1.7 minus 1.3. That is the slope formula, and we get negative 47.5. Okay, so that answers the first part of the question. The second part of the question is, let's estimate the zombie's height at 2 seconds after it's released. So we have an h prime of 1.7, that's our slope. We have a coordinate at 1.7, so we're all primed to use the tangent line equation for a linearization. So this height can be approximated with y naught, which is 54, minus the derivative, plus the derivative, which is negative 47.5, multiplied by t minus x naught, which is 1.7. So there's our tangent line equation. Now to get the estimate for the height at 2 seconds later, we're going to go and just substitute 2 here. And then we simplify. And that gets us 39.75. Let's take a look at that data plotted out. So here are the 3 points where we know the height of the zombie figure. And what we did is we found the slope of the line that connects these 2 points here. The second one here and this third one here. This one and this one. So you see what we're basically doing is we're taking this tangent line here and we're extending, or we're connecting these 2 coordinates with a line. Let me zoom in here. We're taking these 2 coordinates and connecting them with a line and then extending that line downwards. And then we need to figure out where on that line when x equals 2. And there is that point. It is at 39.75. So again, create the tangent line, figure out where on the tangent line you're going to lie when at the points that you're estimating, and that's going to be your estimate, 39.75, which is of course what we got over here. So that takes care of our first day of section 5.5 with our linearization. Good luck, and we will see you in the next video.